In space exploration, in situ resource utilization is the practice of collection, processing, storing and use of materials found or manufactured on other astronomical objects that replace materials that would otherwise be brought from Earth. ISRU could provide materials for life support, propellants, construction materials, and energy to a spacecraft payloads or space exploration crews. It is now very common for spacecraft and robotic planetary surface mission to harness the solar radiation found in situ in the form of solar panels. The use of ISRU for material production has not yet been implemented in a space mission. Though several field tests in the late 2000s demonstrated various lunar ISRU techniques in a relevant environment, ISRU has long been considered as a possible avenue for reducing the mass and cost of space exploration architectures, in that it may be a way to drastically reduce the amount of payload that must be launched from Earth in order to explore a given planetary body. According to NASA, in situ resource utilization will enable the affordable establishment of extraterrestrial exploration and operations by minimizing the materials carried from Earth. In the context of ISRU, water is most often sought directly as fuel or as feedstock for fuel production. Applications include its use in life support either directly by drinking, for growing food, producing oxygen, or numerous other industrial processes, all of which require a ready supply of water in the environment and the equipment to extract it. Such extraterrestrial water has been discovered in a variety of forms throughout the solar system, and a number of potential water extraction technologies have been investigated. For water that is chemically bound to regolith, solid ice, or some manner of permafrost, sufficient heating can recover the water. However, this is not as easy as it appears because ice and permafrost can often be harder than plain rock, necessitating laborious mining operations. Where there is some level of atmosphere, such as on Mars, water can be extracted directly from the air using a simple process such as WAVAR. Another possible source of water is deep aquifers kept warm by Mars's latent geological heat, which can be tapped to provide both water and geothermal power. Rocket propellant production has been proposed from the Moon's surface by processing water ice detected at the poles. The likely difficulties include working at extremely low temperatures and extraction from the regolith. Most schemes electrolyze the water to produce hydrogen and oxygen and cryogenically store them as liquids. This requires large amounts of equipment and power to achieve. Alternatively, it may be possible to heat water in a nuclear or solar thermal rocket, which may be able to deliver a large mass from the Moon to low Earth orbit in spite of the much lower specific impulse for a given amount of equipment. The monopropellant hydrogen peroxide can be made from water on Mars and the Moon. Aluminum as well as other metals has been proposed for use as rocket propellant made using lunar resources, and proposals include reacting the aluminum with water. For Mars, methane propellant can be manufactured via the Sabatier process. SpaceX has suggested building a propellant plant on Mars that would use this process to produce methane and liquid oxygen from subsurface water ice and atmospheric CO2. It has long been suggested that solar cells could be produced from the materials present in lunar soil, silicon, aluminium, and glass. Three of the primary materials required for solar cell production are found in high concentrations in lunar soil and can be utilized to produce solar cells. In fact, the native vacuum on the lunar surface provides an excellent environment for direct vacuum deposition of thin film materials for solar cells. Solar arrays produced on the lunar surface can be used to support lunar surface operations as well as satellites off the lunar surface. Solar arrays produced on the lunar surface may prove more cost-effective than solar arrays produced and shipped from Earth, but this trade depends heavily on the location of the particular application in question. Another potential application of lunar-derived solar arrays is providing power to Earth. In its original form, known as the solar power satellite, the proposal was intended as an alternate power source for Earth. Solar cells would be launched into Earth orbit and assembled with the resultant generated power being transmitted down to Earth via microwave beams. Despite much work on the cost of such a venture, the uncertainty lay in the cost and complexity of fabrication procedures on the lunar surface. The colonization of planets or moons will require obtaining local building materials, such as regolith. For example, studies employing artificial Mars soil mixed with epoxy resin and tetraethoxysilane produce high enough values of strength, resistance, and flexibility param